Right, since we are meeting after some time, let me recall all the things that we've done so far, the topics that we've covered, then we'll move on to today's lesson. We've learned group actions. Let me go over the definition once again. If we take G to be a group and X is a set, we say that an action, the group G acts on X. If I put it this way, an action. P of G on X is a mapping satisfying the following conditions. Is a mapping from G cross X to X such that first phi of G1, G2, X is equal to phi of G1, phi of G2 of X. This is for every G1, G2 that you take from the group and X that you take from the set X. Then phi of the identity times X is equal to X for all X that you take from the set. And we somewhat shorten this notation. Instead of writing these two, we write, G1, G2 dot X, referring to the group action, is equal to G1 dot G2 dot X. This would be the first one. Then we have the identity in the group E dot X to simply equal X. This is how we define the group action, the way the group G acts on a set X. Then we defined the stabilizer for any X that you take from the set, and this is every G that you take from the group that fixes this element through the given group action. So G dot X is equal to X. Every G in G that fixes the element X. And we showed that this is actually a subgroup of G. And we defined the orbit of an element X to be G dot X for every G that you take from the group. And this we showed to be a subset of the set X. Right. And then we showed that if you take all the orbits, they're either, if you take two orbits, they must either be disjoint or identical. And not only that, if you union up all the distinct orbits of the group, or just in general, all the orbits of the group, you should get the set X. And then, yes, we did the orbit stabilized theorem, which I will also state. Which we will use also in today's lesson. If G is a finite group, if G is a finite group and it acts on a set X, we have the number of elements in the orbit of X to be the same as number of elements in G over the number of elements in the stabilizer of X, where X is an element in the set X. Right. Then we actually went over some examples of group actions, some specific examples. major groups where G acts on itself by left multiplication, then by conjugation and all that. If I state some of it, G acting on itself, first by left multiplication, where we define the group action. If I simply write G dot X, where G and X now both come from the group G, is simply given by Gx, left multiplication. So when you say Gx this product, what you see is the group, the binary operation over the group applied to these two elements in the group. And then when G acts on itself by conjugation. By conjugation, that would be G dot X equals Gx G inverse. Yeah, right. These are some of the examples that we went over. This is some important examples. And we say that an element is fixed by the action of the group if for every element G, G dot X is equal to X. That means that particular element in X is fixed by every element in G. In that case, we simply say that it's fixed by the group action. And then we also defined the center of G. Denoted by Z of G to be the set containing X in G, where Gx is equal to Xg for every G, or you can simply write G inverse Xg is equal to X for all G in G. This is what we call the center of G, and it's a normal subgroup in G. Then we defined the normalizer. If H is a subgroup of G, the normalizer of H in G, denoted by N of H, we defined it to be every element G in G such that GH, G inverse, is simply equal to H. This is what we defined as the normalizer. Okay, so with that, we will go to today's lesson. Okay. We are going to start off with a theorem, but before we actually get into the details, let me quickly remind you something that we've done some time back. Let's take G to be a group. Let's take G to be a group. H, a subgroup of G, and K is also a subgroup of G, right? And we define this set HK to contain elements simple H times simple K. Once again, when I say times, what I mean is the binary operation, right? Where H comes from this subgroup, K comes from this subgroup. And observe that this is a subset of G, but not necessarily a subgroup of G. If we have just right, not necessarily a subgroup of G. If we recall, we showed that HK is a subgroup of G, given that H is a subgroup of G and K a normal subgroup of G. This we have shown. But when H and K are simply subgroups of G, HK, this set that we just defined, need not be a subgroup of G. Right. Now, let's define first, let's take this group, this set H cross K, which contains pairs of element where the first component comes from H, the second component comes from K. This set is actually a group under the binary operation of component-wise multiplication. Binary operation of component-wise multiplication. How do we see this? So what does it mean? Now let me quickly write. If we take H1, K1 and H2, K2, these 2 points, 2 elements from the set H cross K, right? Then if I define this by, I will simply denote by star the binary operation. This would simply mean we multiply component wise. So we have H1 times H2, K1 times K2. Now in this case, when I once again say H1 times H2, this times actually refers to the binary operation of G that is defined over G. So this is component-wise multiplication. This is a binary operation over this set. Together with this binary operation, this defines a group. Right? The associativity property holds, you can see this clearly if you write it out for these 3 elements that you take from here. If we do H1, K1, star H2, K2, star H3, K3. If we perform the binary operation over these 2 first, we have H1, K1, star. By definition of the binary operation, we've got H2, H3, K2, K3. We simply multiply component-wise. Right. Once again, applying the binary operation, we see that this ends up being H1, H2, H3, K1, K2, K3. This is equal to H1, H2, K1, K2, star, H3, K3. Once again, by definition of this binary operation defined over this set. Now this you can write as H1, K1, H2, K2. So the associativity property holds. And the identity is given by the identity E, which is an element in H cross K. Why do we have this? Observe that H is a subgroup of G. So the identity that's in G, now this identity is the identity in the group G. Because H is a subgroup of G, E is an element in H. Once again, because K is a subgroup of G, E is also an element in K, which is also the identity. Now observe, if we take H1, K1 and apply the binary operation to this element containing the identity in each component, we have H1 times the identity, which is simply H1, K1 times the identity, once again, K1. And this is equal to identity H1 times identity K1, which is simply identity star H1 K1. So the identity of this group is this, where each component is the identity of G. Now, inverse of H1 K1 in H cross K. It's easy to see that the inverse of this element is given by the inverse of each component, right? This is because if you take H1 K1, apply the binary operation to H1 inverse, K1 inverse, what you have is H1 times H1 inverse, K1 times, K1 inverse, which ends up being the identity. And you can commute these two and see, once again, we get the same thing. So we see that by definition, this is a group. Is a group. Right. So this is a group. HK, is a subset of G. Now, we are going to define an action. We are going to define an action of over H times K. So let me write it this way. Let H cross K act on HK as follows. Let's take HK, an element from here. Dot, once again, in the usual notation, denotes the group action. And this simple X is taken from the set HK. And the group action we define to be H times X times K inverse, right? Now, when I say once again, H times X times K inverse, this multiplication that you see over here is actually the binary operation over the group G, because all these elements are actually coming from G. H is a subgroup of G, K is a subgroup of G, this is a subgroup of G, this is a subset of G. So every element that you actually see, H, X, and K, and even its inverse are elements in G. Right. Now observe this action. This action is actually well defined. Let's prove it. This action is well defined. Since if you take two elements, H1, K1, H2, K2 from H cross X, and if those two are equal, since so H1, K1 equals H2, K2, we have H1, K1 equals H2, K2 if and only if H1 is equal to H2 and K1 is equal to K2. These 2 points are the same if their components are the same, right? This is if and only if mm, uh, if we take the group action of H1K1 with X, we must have H1X K1 inverse to equal because H1 is equal to H2, H2X K2 inverse for some or for any X, not for some, for any X that you take from the set HK, right? And this is if and only if you go to the definition of the group action, we must have H1 K1 dot X to equal H2 K2 dot X. So by definition, we see that the action is well defined. Not just, we also must show that this is in fact a group action. And in order to show that this is a group action, we have to show these two conditions hold. So let's take H1, K1, H2, K2 from the group H cross K. Then we have H1, K1 dot H2, K2 dot X for X in the set that you take to equal H1 K1 this component dot. First we apply the group, the group action over here so that we get H2X K2 inverse, right? And this is for X in the set HK. This is equal to once again applying the group action to these two elements. This an element in HK, this is an element in H cross K. We see that this ends up being H1, the element which is H2X K2 inverse, which comes from HK, times K1 inverse. Now what do we do? Using the associate, now observe that this is an element in G. H1, H2, X, K2, K1, they're all elements in G. So now we are using the associative property. We see that this ends up being H1, H2, X, K2 inverse times K1 inverse. Taking the inverse out, we see that this ends up being K1, K2 inverse. K1, K2 inverse. Now, this is equal to H1, H2 and is an element in H. K1, K2 is an element in K. So once again, by definition of the group action, right? We see that this is equal to H1, H2, K1, K2 dot X. So, we see component-wise multiplication over here. When you go to the group binary operation of H cross K, we see that this is equal to H1, comma K1. I will simply write it as a product instead of putting the star. We understand it's simply the group binary operation. H2, K2 dot X. Right. So the first condition is satisfied, and then to show the second condition, for the identity that's in the set, that's in the group H cross K, and any element X that you take from the set HK, we have this identity element, sorry, in H cross K dot X. By definition of the group action, this is simply identity X, identity inverse. Identity times X is simply X. Inverse of the identity is the identity itself. Once again, X times the identity is X. So this is a group action because it satisfies the given two conditions. Right. Now observe one thing. Let's try to find the different orbits in this over this set HK. Right. Observe that what I'm going to do is I will show that there is only one orbit under this group action. And in order to do so, we will find the orbit of the identity. Orbit containing the identity. Observe that the identity is equal to identity times identity. Identity times identity is an element in HK. Right? So the identity is an element in the set HK. H is a subgroup of G, therefore the identity is an element in that. K is a subgroup of G, identity is an element in that. Identity, when you take the binary operation with itself, gives you the identity, right? Right. Now, the orbit of the identity is given by, if you go back to the definition once again, you take any element from the group, take the group action by this element. In our case, we are going to take it by the identity. So we take any element HK from the group H cross K dot the identity, where HK comes from the group. By definition of the group action, this is equal to H, the identity K inverse. Comes from H cross K. Now this H times the identity is HK. So this actually contains elements HK inverse, where HK is an element in H cross K. Now observe, what I'm going to do is show that the set HK is a subset of this orbit from this definition. Anyway, by definition of an orbit, we know that this is a subset of HK, right? Now this contains elements of this form. Now observe, we will show that, let me first write, we will show that HK is a subset of this particular orbit. Right. So in order to show this, let's take any element from the set HK. So let's take H naught, K naught from the set HK. Right? Then observe that we can write H naught, K naught as H naught times the identity times the inverse of the inverse, right? The inverse of the inverse. Now, what does this mean? If you go back to the definition of the group action, right? When you take H naught, K naught from the set H times K, that means H naught is coming from H by definition, K naught is coming from K. So H naught comma K naught, that point is in this set, right? So what we've done over here, if you go back to the definition of a group action, is taken the group action of H naught, K naught inverse with the identity, right? Because K naught is an element in K is a subgroup of G, its inverse is also an element in K, right? Now we see that this element is an element in H cross K, and we have taken the group action by the identity. If you go to the definition of the orbit of the identity, we take elements of H cross K and take the group action with the identity. So what you see over here is an element in the orbit. Therefore, H naught K naught is an element in the orbit of the identity. Because this is chosen arbitrarily, we see that HK is a subset of the orbit, and the orbit of the identity will always be a subset of HK. Now that we've shown HK is a subset of this orbit, this implies the orbit of the identity is the entire set. The entire set. And we already know if you take any two orbits, they are either disjoint or identical. And not only that, you union up all the orbits, you get the entire set. From just one orbit, you get the full set HK. This means there is only one orbit, and this orbit is given by this. Any element in the set will generate the same orbit. Okay, there is only one orbit. Okay, let's also find the stabilize of this argument. Now, let's find stab E. Okay. Stabilize of this identity by definition is every element in the group that fixes the identity. So HK that is in our group such that will fix this element identity. It has to be written like this. HK dot E is equal to E because the identity has to be fixed here. H comes from the group, subgroup H. Simple K comes from the subgroup K. Now we further simplify this by applying the group action. This gives you H times the identity times K inverse equals the identity. So H is in H, K is in K. So we are taking HK, these points. Now multiplying both sides in this equation on the right by K, we see that HE is equal to EK, where H is taken from H, K is taken from K. HE, H times the identity, by definition of the identity is simply the element H, E times K is K. Now we see that H is equal to K. H comes from this group, simple K comes from this subgroup. Now H is equal to K, so what we are going to do is replace this K by H because they are the same, right? Now observe H is in H, and this K over here, once again, I will replace by this. What sort of elements do we have? H, where H comes from this as well as K. In other words, it contains every element such that H is in the intersection of these two. The intersection of these two. So this implies, right? No, let's stop here. Let's go back to the theorem that I wanted to state at the very beginning. Now we see that the stabilize of the identity gives all these. Right, let me state the theorem. Okay, let H and K be subgroups of a finite group G then the number of elements or order of the set HK is equal to the number of elements in H times number of elements in K over the number of elements in H intersection K. Now observe, G is a finite group. H and K are subgroups of G. So their orders also must be finite. Therefore, all these numbers that you see over here, they are finite, right? Okay, now we have to show that this equality holds. Okay, from all these that we've done so far, right? All these that we've done so far, we have defined a group action use with the group H cross K, and it acts on HK, which is given by this, right? So this is what we are going to use now, right? This is what we are going to use now to prove this, and we will employ the orbit stabilizer theorem. Right. So let me write, we've seen that H cross K act on HK as dot x equals Hx K inverse, and also the we have seen that the orbit of the identity is the entire set HK. In other words, there is only one orbit. Right? There is only one orbit. So now from orbit, and not only this, and we've seen that the stabilizer of the identity is given by elements of this form, where H actually comes from this intersection. When you see that the stabilizer of the identity is this, we can deduce the number of elements in the stabilizer must equal the number of elements in this intersection. Now, this intersection is finite, therefore, this also contains a finite number of elements because G is finite. Now, the stabilizer contains elements of the form H comma H, where H comes from the intersection, right? So the number of elements in the stabilizer is the same as the number of elements in this intersection. When you see that the orbit of the identity is equal to the set itself, the number of elements in the orbit is the same as number of elements in HK. Now what do? We use the orbit stabilizer theorem. If you go back to the recap, the orbit stabilizer theorem tells you the number of elements in the orbit of X, where X is an element in the set, is equal to the number of elements in the group G over the number of elements in the corresponding stabilizer when G is a finite group. In our theorem, G is given to be a finite group, so we can employ the orbit stabilizer theorem, right? For the identity that is in HK, right? Since G is finite group, and E is in HK by orbit stabilizer theorem, we see that the elements in number of elements in the orbit of the identity is equal to the number of elements in H cross K. Right now, when G is finite, I should have written over here. This tells you H cross K is also finite. This is also finite, right? So we are going to apply the orbit stabilizer theorem for the finite group H cross K, which is acting on H times K, right? So the orbit stabilizer theorem tells you for identity E, which is in HK, the orbit of that, the number of elements in it, is equal to the number of elements in the group that is acting on HK, which is this, over the corresponding, the number of elements in the corresponding stabilizer, which is stab E, right? Now from here, because the orbit of the identity is equal to the entire set, the number of elements in here is the same as the number of elements over here. We must have HK, number of elements in HK, and the number of elements in H cross K is the same as number of elements in H times the number of elements in K. You don't have to write this, you simply write it there. But we are referring to over here is simply the product. Over, from here, we see that this is the number of elements in the intersection. And which is exactly what we wanted to show, right? If we go over this once again, G is given to be a finite group. We are simply taking the subgroup of G, which is H cross K, and we defined its action on the product HK given over here. And then because G is finite, the subgroup H cross K is finite, even HK is finite. From the previous statements, we see that the number of elements, there is only one orbit in the group under this group action. So the number of elements in that orbit is the same as the number of elements in the set. Using the orbit stabilizer theorem, we get the result. Not only that, we proved early on that the number of elements in the stabilizer is the same as the number of elements in the intersection of the two sets. Okay, let me quickly note down some things. The length of an orbit is what we call the number of elements in an orbit. Number of elements in an orbit. Points is what, points when we say point or points, we refer to the elements in X. Now we write Burnside's lemma. Let me state this first, then we will go over the proof. We take G to be a finite group which acts on a set X. G act on a finite set X with R number of orbits. Let's suppose this has R number of orbits. Then we have R to equal 1 over the order of G. Remember, G is a finite group, so it has at least one element. 1 over G times the summation let me write it will first, then I'll define it. I forgot to write. Let me quickly write this definition on the other side. No, let's write it over here itself. Okay, what do we mean by this? Right, let me write the definition. Should have written it earlier. Okay, let's take G to act on X, and let's take any element G. Let me write, let G act on the set X given any element G in this group, the set of elements in X fixed by G is denoted by fix sub G of X, right? That is, we take, for this particular G, we take every element in the set X that are fixed by this element G. So if you write it, fix G contains elements X, which comes from the set, which are fixed by this particular G, right? Then now observe that if you take all the fixed points, right? If you take all the fixed points in the over this group action, what you get are the points that are fixed by every element in G. So it's easy to see that the set of all fixed points would be the intersection of all these sets. You let me write, it is easy to see that. The set of all fixed points is equal to the intersection of all these. Why do we have this? Now see the difference. In here, we are simply collecting elements in X that will be fixed by this particular G. When you say fixed points, those are the points that are fixed by every G. So what we do is we take all these sets, right? And we collect all the common elements. The common elements meaning elements that are fixed by every G. So the set of all fixed points must equal the intersection of all these sets. Now going back to this lemma, where G is a finite group acting on a finite set X with R number of orbits, we see that R is equal to 1 over G times this summation. The summation meaning for every G we are taking, for each G we are taking the elements that are fixed by it from X, right? So in other words, what does it really give you? R resembles, or the number of orbits actually is the uh, sort of like the average of fixed points of the elements that are in the of the group G. If I write it, so this means by this equation we can see that the average, the number of orbits gives you the average of the number of fixed points of the elements of the group G. Right. How do we prove this one? So let's go back to the proof now. Okay. So the proof. First, let's consider the set. First, consider the set uh, given by G, comma X containing all these elements that come from, let me write, that come from G cross, sorry, G cross X, comes from G cross X, where G dot X is equal to X. So we are taking points from the set G cross X, right? We are taking elements from the set G cross X. Elements are of this form. We are taking one, this first component comes from the group. The second component of this element comes from the set X. How do we pick these pairs? We pick the pairs so that this particular element G fixes whatever the element that you take from the set X. In other words, G dot X is equal to X. We pick the pairs of elements Gx such that G dot X is equal to X, where G fixes X, right? If I simply, right. Now what we are going to do is let's fix G. Now let's fix G. Now G is fixed, but X could be varying, right? Now in this set, what we are going to do is we are going to fix G. So we will have, this is some examples for you all to understand, not necessarily a part of the proof. Now we are fixing G. For example, if we fix G naught, so we take G naught x1, that will belong in this set. If we take G naught x1, which is an element in this set, this means G naught dot x1 is equal to x1. Then we could have another element, maybe G naught x3, right? It doesn't have to be in this format, x1, x3, just for your understanding. If it is an element in this set, then we must have G naught x3 equals x3. So now in this set, we have elements where G naught is fixed, but we are taking all the pairs where x, which comes from the set x, is fixed by this particular G naught, right? So all the x's that are coming from these elements, right, that are coming from these pairs are elements in the set X that are fixed by G. So if you go to this definition, when we pick pairs, when you fix G naught in this set, that means we are picking pairs Gx, where X is fixed by this particular G. So we understand once you fix G in this set, the number of elements that you get over here is the same as the number of elements that you get from this set. This is when you fix G, because in each pair, the first component will not change. The second component, however, will be changed if the second component or these elements are fixed by G naught, right? If they are fixed by G naught, these elements will also belong in this set where G is simply replaced by G naught. So we see that once you fix this particular G, the number of elements in this set is the same as the number of elements in fixed sub G of X for this particular G, right? So let me write. Then clearly we must have number of elements in the set Gx, where G dot x is equal to x. When G is fixed, this is okay, is equal to the number of elements in fixed G of x. Particular G. Okay, so we have this. Right. Now we fix G, vary x, and we notice the number of elements in this set is the same as the number of elements in this. Now suppose we vary both G and both G and X, right? Now when G and X both vary, we must have, for example, now when G is fixed over here, this is equal to this one. Now what I'm going to do is I will take G, now this is say G naught. Now we change that to G1. Now when G1 is fixed, once again we get the elements on this side to be, sorry, not on this side, the number of elements of this set, when G is simply replaced by G1, because we have to vary G as well now, the number of elements of this set would simply be the same as the number of elements of fixed sub G1. And when you vary G into G2, once again, we see this will be replaced by G2, this over here by G2. So you see, when you vary G and both X, the number of elements in this set that you get where G dot X is equal to X is the same as the summation of all these um, orders. So we see this is equal to when G varies, the number of elements over here. This is when both G and X vary, right? Okay. Let's take this to be, get to be 1. Okay. Now what we are going to do is go back to this set. Now we are going to fix X in this set. Let me write the set first, G comma X. Okay. Now we fix X and see that the number of elements in the set when X is fixed is the same as the number of elements in the stabilizer of X. If you recall, I'll just write it over here. Step X gives all elements in G that fixes this particular element X. That is G dot X is equal to X. So in the stabilizer of X, we take every element from the group that fixes this particular X. Now, if you go to this set once again, when you fix X over here, X does not change. However, G changes, right? G changes. How do we see this change? We consider all possible G's so that in these pairs of elements that are in this set, only the first component will be changed if it fixes X, right? So every G that appears in the stabilizer will appear in the first component of all the points that are in this set when you fix the X, when you fix this particular X. So the number of elements over here is the same as number of elements in this set when X is fixed, because in each element, the second component is fixed. Only the first one is varied according to this condition. So it's easy for us to see that. When X is fixed, the number of elements in this set is the same as the number of elements in the stabilizer. Okay. Right. Now, once again, keeping this in mind, we change both X and G. Hence, when G and X both vary, we have the number of elements. Now, X is fixed, G varies. Now we take another X and find all possible values. Then we take fix another X, find all possible values. Likewise, then you see this clearly gives you the number of elements in this set where G dot X is equal to X to be the same as the summation of the number of elements in each stabilizer, right? So the summation when it runs through this sets, which we will take to be 2. Right. Now, from 1 and 2, we see that the order of this set is the same as this summation. Order of this set is the same as the summation when taken over all the stabilizers, right? Every element in X, and for each of those, we take the orders of each stabilizers. Then by 1 and 2, we get this equation, equality, equals, well, now what do we do? G is a finite group. Therefore, it has at least one element and a finite number of elements. We divide both sides by the order of G. Order of G is at least 1. We divide both sides by the order of G. We divide both sides by the order of G. We have 1 over the order of G same as. Now, what I'm going to do is I will take the order of G inside this summation and write over the order of G. Right. Now, if we go back to the statement of the theorem, again, we are almost done now. We have gotten the right-hand side of the equality. We only have to show that R is actually equal to this part. We are almost done. Now we only need to show that R, the number of orbits, is equal to this summation. This is what we have to show. If once we show this, we are done. Right. Now what we are going to do is, given that G is a finite group, we will employ once again the orbit stabilizer theorem, right? Because we have written G is finite over here also, so no need to write it again. But since G is finite by the orbit stabilizer theorem, we see that the number of elements in the orbit X is equal to the number of elements in G divided by the number of elements in the corresponding stabilizer. That means stabilizer of X. Now, we want to get this quantity. So this implies that the number of elements in the stabilizer of X over the number of elements in G is the same as 1 over, we are simply taking the reciprocal, right? Orbit of X, right? Orbit of X. Therefore, this entire equation reduces to 1 over the order of G, summation when take over all elements G's, X sub G of X is equal to the summation of this. The summation of G, X. Right. Now, we are changing X in each X, right? Say we take a single orbit, we simply take a single orbit. And if you, for each X, right? Or in other words, if when the element X run over a single orbit of length let's say M, it has M elements, right? It has M elements. Then we see that because any element that appears inside this one orbit, if any two elements are in the same orbit, and when you find the corresponding orbit for those two elements, you get that same orbit. For example, if X, X, Y are in orbit of, let's say, Z, this implies that orbit of X is equal to orbit of Y is equal to the same orbit Z, right? So when you when you take just one orbit and you run over each element of those orbits, for each element, when you find the orbit, you get the same orbit. That's what I'm trying to say. For example, in this, you consider the orbit of Z. And inside this orbit, you have the elements X and Y, right? So take this X, you find its orbit, you get once again the same orbit Z. Take this Y, you find its corresponding orbit, which is orbit sub Y. You get the same orbit, which you started off with, orbit of Z. So inside one orbit, when you run over the elements in it, right, you get the same orbit. So what do we have in this summation? In that case, for every element that you go, let me write it. Once I write it in equation form, it's easy to see. Let's consider a single orbit C of length M. Let's take the length of this orbit to be M. In other words, it has M elements in it. Then if you go back to this sum, because we are trying to find a value for this sum, instead of taking X from all over the set X, we are simply going to consider X that are in this one orbit. We have the summation where X comes from this single orbit of 1 over the number of elements in orbit X is equal to, for this for one particular X, right, the orbit of X is the same as C, because this X is coming from C. The same thing that I told you over here as well. If you are taking elements from the same orbit and find their corresponding orbits, you get this same orbit. Even though we are changing the index over here, the elements that are inside this orbit are the same, right? So we have, for each X that you take from inside the orbit, the number of elements in it will always be M, because this orbit is of length M. So we have 1 over M plus 1 over M, likewise plus 1 over M. How many of these are we actually, how many are we summing up? M terms, because there are M number of elements. So in the summation, we have M terms. So this becomes M times 1 over M, which is simply equal to 1. Which is simply equal to 1. Right? Now, because the entire set X has R number of distinct orbits, this is the order for some orbit C, right? And we have R number of such orbits. And remember, this C is taken arbitrarily. So for any orbit that you take, the summation that you take from this set, summation will always end up being 1, right? And you have R distinct orbits. So when you take the full summation, When you take the full summation, you have R times 1. So let's write since X contains R distinct orbits, we get, when you take the count and when X runs over all these, the full set, is equal to R, right? Because we are adding up 1 R times. And so we have, if we go back to this equation, this side will simply be replaced by R, and we conclude the proof. And so we have R. Okay. Now let's get to another definition. Right. We say that group G is a P group if the order of G is a power of some positive, non-negative power of P, where P is a prime. So let me write. So let me write a group G is said to be a P group. If the order of G is equal to P to some power of K for some prime P and a non-negative integer K. Okay. So non-negative integer K. So K is either 0 or a positive integer. If K is equal to 0, P raised to the 0th power is simply 1. In that case, G is the trivial group containing simply the identity. When K is not equal to 0, this is some non-trivial group. Right. Theorem. This we give it a special name, the fixed point congruence. Let me write the statement. Let G be a finite P group. That means by definition, its order is some power of P, some non-negative power of P, where P is a prime number. P group acting acting on a finite set X. Let G be a finite P group acting on a finite set X. Then the number of elements in X, remember G is a finite P group, X is a finite set. Number of elements in X is congruent to the number of fixed points modulo P, which we simply write as mod P. Right. Now, this is not relevant to the proof or the theorem statement, but to give you a quick idea about congruences, what does it mean if you have any two integers x and y, right? We write x is congruent to y modulo d, x congruent y mod d. We write this if and only if d divides x minus y. If and only if d divides x minus y. So over here we have the number of elements in X to be congruent to the number of fixed points modulo P. In other words, the number of elements in X minus the number of fixed points must be divisible by P. Right? This is what we have to show. So, if you go back to the theorem statement, this means, or we can write that is, P divides the number of elements in X minus the number of elements in this set. This is what we have to show, that P is a divisor for this quantity. Right. Let's go to the proof. X is a finite set, right? So what we are going to do in this case is we will pick the finite or the distinct orbits in X. So let's write that orb x1, orb x2, and orb x r maybe be the set of distinct orbits in X. Then we have, if these are the distinct orbits in X, we know X is the union of all these distinct orbits, right? Then we have X to be the union where I goes from 1 to R of these orbits xi, so that the number of elements in X is the same as the number of elements in the summation of the number of elements in each of these distinct orbits. Now remember, we know that you take any two orbits, they are either disjoint or identical. They have no intersection. If there are two, so it's in the statement itself. They are either disjoint or identical, right? So the number of elements in X is the same as the summation of the number of elements in all these orbits, distinct orbits, that is. We have this. Okay, now G is given to be finite. So once again, we are going back to the orbit stabilizer theorem. since G is finite, by the orbit stabilizer theorem, we know the number of elements in an orbit xi is the same as the number of elements in G over the number of elements in the corresponding stabilizer. So step of xi, right? Now observe that if the number of elements in any of those orbits is equal to 1, that means it has only one element. If the number of elements in any of these xi's is equal to 1, then this is if and only if, because then from the orbit stabilizer theorem, we see that the number of elements over here is equal to the number of elements G divided by number of elements of the corresponding stabilizer. This is if and only if this quantity that you see on the right hand side of the equation is equal to 1 if and only if number of elements in G is equal to the number of elements in the corresponding stabilizer. This means G must equal the corresponding stabilizer. Right, so this is if and only if G is equal to this corresponding stabilizer. Why do we have this? We know by definition of the stabilizer, it is a subgroup of G. We have proved this in an earlier class. When the G is the stabilizer of any element is a subgroup of G, and with this condition, if the number of elements in G is the same as the number of elements in the corresponding stabilizer, we have only one option, that is G being the same as the stabilizer, or the stabilizer being equal to the group itself. This is because since Xi is a subgroup of G, and G is finite. G is finite. Right. Now, if the number of elements, so from this we get that if the number of elements in any orbit is equal to 1, G equals the corresponding stabilizer. The corresponding stabilizer is G itself. On the other hand, if any stabilizer is a proper subgroup of G, if it is a proper subgroup of G, then we must have the number of elements in the corresponding orbit to be different from 1, because this is an if and only if statement. If the stabilizer is a proper subgroup of G, that means it's not equal to G, then we can't have this order to be equal to 1, right? So if I write it, if step xi is a proper subgroup of G, then the order of the corresponding orbit cannot equal 1, and we know this is equal to the number of elements in G over the number of elements in the corresponding stabilizer. And we say that if this is the case, the order of the orbit must be divisible by p. Must be divisible by p. And to see this, why do we have this condition? Because G is a G is a P group. That means G is a P group. Let me write it. Because stabilizer of Xi is a subgroup of G. And because G is finite, this stabilizer is also finite. And so by Lagrange's theorem, we know the order of the subgroup stab of Xi divides the order of the group G. This means now G is a P group, right? G is a P group. Therefore, it is a power of some non-negative power of P, right? And when this is a subgroup and it divides the order of G, which is a power of some prime number, the only possibility would be for the order of this also to be a power of the same prime number, right? Now G is a P group. That means the order of G is the power of some prime, non-negative power of some prime number P. If we have another number that divides this power of the prime P, this number also must be a power of this same P, right? Therefore, we must have the order of the stabilizer to equal pi for some I that is greater than 0, less than, between 0 and k, right? Between 0 and k. Therefore, we have that the order of orbit of xi, which is not equal to 1 by the way, equals order of G over the order of the stabilizer. Order of G we have taken to be P to the power of K, this P to the power of I, P to the power of K minus I. Because I is less than K, K minus I is greater than 0, right? Greater than 0. Therefore, right, P divides the number of elements in this orbit. Remember, the order is now not equal to 1. It's some number greater than 1. With this clarification, we see that P actually is a divisor for this order. Now, what we have to show at the end is that P divides the number of elements in X minus the number of elements in the set of fixed points. Now, number of elements in X is equal to, remember, X is the union of all orbits in it, right? So, we can take this to be this summation. Wait, I think I will refer to this one. Now this summation, sorry, we have already written the summation. This summation, what we are going to do is we will break or we will group where the orbits have just one element, where the orbits have more than one element, right? So this summation, what I'm going to do is I will rewrite it as order of X, where we group the summation into two. number of elements in orb xi is equal to 1 plus where the number of elements in the orbit is not equal to 1. Right? So this this will simply be replaced by 1 because in this summation we are simply collecting all the orbits or the orders of orbits where the orders are 1. Right? So this summation, in this summation we have each term to be 1. Plus, now when the order of the orbit is not equal to 1, we have shown that P divides its order. So this means the order of, orb of xi is a multiple of P. So I'll take it to be P alpha. This is an integer, right? P alpha. So this will be I'll take it, yeah, let's take this to be. Then this summation ends up being P times M. In other words, we are adding, if I take this, not just alpha, I'll put it as alpha I. So for each I, we have P alpha 1 maybe if orbit of x1 is having order not equal to 1. That is, likewise, we are taking all these orders, we add it together, then we have P times some integer. So I'll take that integer to be n. So sum m in Z. Now observe, we see that all these are finite numbers. So we can write order of x minus the summation that you see. What we are actually doing is bringing this summation to the other side. Okay? Is equal to P times N. So what you see on the left is a multiple of P. What does it mean? That means this quantity is divisible by P. If you go back to this definition of, with respect to these congruences, if D divides the difference x minus y, that means x is congruent to y modulo D. Over here, P divides this difference, order of x minus this quantity. So this means, this implies order of x is congruent to this summation modulo P. We are almost done. All we have to show is that this quantity ends up or is the same as the number of fixed points, right? That number is the same as the number of fixed points. Okay. Now, let's take the orbit of xi if its order is equal to 1, right? This means this is if and only if and only if the orbit of xi, by definition, all, if you go back to the definition, this means this is simply containing the point xi for all g in G. What sort of elements do we have here? We have G dot xi for every G in G. If you go back to the definition, which we recalled early on, the orbit of any element x is simply g dot x for every g in G. And we know, we have seen in earlier lessons that the orbit of x, orbit of any element, will always contain that element. Why is that? G is a group, it has the identity dot x simply gives you the element x. So x is always an element in its orbit, right? And if the order of the given orbit is 1, we surely have that one element to be the corresponding xi, right? To be the corresponding xi. That means, by definition, xi must equal g dot xi, because this is the only element now in the set, for all g in G, right? Now, this xi is equal to g dot xi for every g. So what does it mean? By definition, xi is a fixed point. Xi is fixed, right? Therefore, for each of those xi's where the order of its orbit is equal to 1, that xi is fixed, right? So in this summation, we contain the number of fixed points corresponding to each such orbit with order 1. Hence, we have the summation actually be to the number of equal to the number of fixed points, right? So all we have to do is replace this summation by this quantity. So the theorem follows. I'll simply write. Okay, next we have this corollary. Let G be a finite P group acting on a finite set X. So G is a finite P group acting on a finite set X. If the number of if the order of X, or the number of elements in X, is not divisible by P, then there is at least one fixed point in X. Then there is at least one fixed point in X. On the other hand, if the order of X is divisible by P, then the number of fixed points is a multiple of P, possibly 0. Possibly 0. Okay, let's get into the proof. Now you are given G to be a finite P group, which is acting on another finite set X. Then the order of G by definition is Pk for some non-negative number K, and X is finite. First statement is, if the order of X is not divisible by P, then there is at least one fixed point in X. So let's assume the number of fixed points in X to be 0. In that case, we must arrive at a contradiction. We're simply going to use the method of contradiction. Right? I'll take it as 1 and 2. Let the number of fixed points in X be 0. Right? What does it mean? The order of this set, fixed points, is equal to 0. If you go back to the fixed point congruence, now we have assumed that the number of fixed points is 0. This quantity is 0. So because G is a finite P group acting on a finite set X, right? Acting on a finite set X, we see that using the fixed point congruence, we can conclude the order of X is congruent to 0 modulo P. Then by fixed point congruence theorem, order of X is congruent to 0 modulo P. What does it mean by definition of these congruences? This means, this is if and only if order of, X. Let me write it. This means that P divides order of X minus 0. This 0 by definition. Here, if we go back to this, X congruent Y modulo D means D divides X minus Y. In this case, Y is 0 in our case. So this means P divides the order of X, which is a contradiction because we are given that the order of X is not divisible by P. Which is a contradiction, as order of X is not divisible by P. Therefore, the assumption itself is wrong. It's we must have at least one fixed point. Not all, we can't have the number of fixed points in X to be 0. We must have at least one fixed point. Therefore, there is at least one fixed point in X. Right, now to prove the second one. This is if the order of X is divisible by P, then the number of fixed points is a multiple of P or possibly 0. So once again, we can employ the fixed point congruence because G is a finite P group acting on a finite set X. That is exactly what we are going to do. by the fixed point congruence theorem. We know that the order of x is congruent to the order of the set containing all fixed points modulo p, mod p. We are given that order of x is divisible by p. We are given that p divides the order of x, right? Then, using the language of congruences, we see that x is congruent to 0 modulo p, right? X is congruent to 0 modulo p. So from number theory, you must have learned, so with respect to the modulus p, x order of x is congruent to 0. So in here, in this congruence, we simply replace the order of x by 0, right? So we have 0 congruent to this. Modulo p. And the other property that you must have learned is if A is congruent to B modulo P, then we must have B congruent to A modulo P, right? 0 is congruent to this number modulo P, then we must have this congruent to 0 modulo P. This is congruent to 0 modulo P. What does it mean? This means P divides this number. By definition, we have P to divide this order. Right? In other words, if P divides this, the order of the set containing all the fixed points, that means the number of fixed points is a multiple of P. Therefore, is a multiple of P. Okay. Right, let's do a small theorem and then we'll finish off for today. Let me write the statement. Now let's take G to be a non-trivial P group. That means G is not the trivial group. In other words, because G is a P group, if the number of elements in G is some power of P, some non-negative power of P, but because we are specifically given that it is non-trivial, it has to be some positive power of P, right? Then the center Z of G is non-trivial. Z of G is non-trivial. Right. Because G is a P group, we can write G as a power of pk. Here, k has to be greater than 0 because g is non-trivial. Right? I'll just, it doesn't really, you don't have to write it out, but for your understanding, I'll put it here. Since k equals 0 implies that order of g, this is, order of g is simply p raised to the power of 0, which is 1, implying g is the trivial group. That's why we have to have k to be a positive number, not just a non-negative, excluding 0, that is. Right. Now to show that this is non-trivial, we consider the action of G on itself by conjugation. This is where the proof really starts. Consider the action of G on itself by conjugation. That is, G dot X is equal to GXG inverse, where G and X both are elements in G, both elements in G, right? Right. Now observe, X is a fixed point if and only if X is equal to G dot X for all G in this group. This is if and only if X is equal to, by simply applying the group action, GXG inverse for all G in G, right? By multiplying both sides on the right by G, you see that this is XG is equal to GX for all G in G. In other words, by definition of the center, we see that X belongs to the center of, X belongs to the center of the group Z of G. So what does it tell you? All the fixed points are elements of the center. Every fixed point is the element, is an element in the center. Every element in the center is a fixed point, right? Therefore, we have fixed points are the elements of the center. Therefore, order of this set, fixed points in G now, because our set G is acting on itself, is the order of G's center. Now, using the fixed point congruence theorem, we see that the number of elements in G, observe that if you go to the fixed point congruence, G, a finite P group acting on a finite set X. Now in our example, G is acting on itself. So X is G in this particular case. That's why instead of the order of X, we have order of G, right? Order of G is congruent to the order of the fixed point, the set containing the fixed points. Because we have shown that this is equal to this, we have Z of G modulo P. Now, G is a P group, right? Since P divides the order of G. G is a P group, right? We have order of G to be congruent to 0 modulo P. So we replace this quantity by 0 and same as before, if 0 is congruent to the order of Z of G modulo P, we must have the order of Z of G be congruent to 0 modulo P. In other words, P divides the order of Z of G. Now, the P is a prime number, so it's the minimum number it could be is 2, right? It's either 2 or some number greater than 2. Some other prime, that is some other odd prime, okay? So the order of Z of G cannot be 1 because P divides this order. This means, with this we conclude, and hence the order cannot definitely be 1. Z of G cannot be the trivial group, the trivial subgroup of G. So it's non-trivial because P divides its order. With this, I will end today's lesson and we'll continue from here the next day.